I'm continuing with the work. I'm sorry. I was talking about work, and it says work has two places, force and displacement. And I was given an example of force, like a father pushing the grocery cart down the sill of a grocery store, a freshman lifting a backpack full of books upon his shoulder, a weightlifter lifting a b-ball above his head, an Olympian launching a shot put, etc. In each case, I'm giving an example. I've given an most example. So here are some example you need to describe. It says read the following five statements and determine whether or not they represent example of work. Then then see if it's correct. So let's see. A teacher applies a force to a wall and becomes executed. Is it a work? I think yes, it's a work. A book falls off a table and free falls to the ground. In this case, it's no. A waiter carries a tray full of meals above his head by one arm, straight across the room at constant speed. Carefully, this is yes, it's a work. It's a work. Uh, let's work. Let's difficult question that will be discussed in more details. Um, Mathematically, work can be expressed by the following equation. Mathematical work can be expressed by equation. This equation. It says W equals to force times displacement times cosine. And where F is the force, D is displacement, and the angle theta is defined as the angle between the force and the displacement vector. Perhaps the most difficult aspect of the equation above is the angle theta. The angle is not just any angle, but rather a very specific angle. The angle measured is defined as the angle between the force and the displacement. To gather an idea of its mean, consider the following three scenarios. Scenario A: a force acts right. A force acts rightward upon an object as it is displacement rightward. In such an instance, the force vector and the displacement vector are in the same direction, though the angle between force and distance is 0 degrees. Scenario B: a force acts leftward upon an object that is displaced rightward. In such an instance, the force vector and the placement vector are in the opposite direction, though the angle between F and D is 180 degrees. Scenario C: a force acts upwards on an object as it is displaced towards rightward. In such an instance, the force vector and the placement vector are the right angles to each other, though the angle between F and D are 90 degrees. So this is the let's draw this. I think that this artwork will define. Ah, that's the force, that's the displacement, and this is the angle. So whenever F whenever F and D are in the same direction. So whenever F and D are in the same direction, the theta is 0 degrees. Whenever it is to do work, force must displacement. So let's consider scenario C. It's C above a model. Scenario C involves a situation similar to the waiter who carried a tray full of meals above his head by one arm straight across the room at constant speed. It was mentioned earlier that the waiter does not do work upon the tray as he carries it across the room. The force supplied by the waiter on the tray is an upward force, and the displacement of the tray is a horizontal placement. As such, as such, the angle between the force and the displacement is 90 degrees. So it's 90 degrees up straight of the tray. Is like if the work done by the waiter on the tray were to be calculated, then the result will be 0, regardless of the waiter on the tray of the magnitude of the force and displacement. So this was how we are going to calculate it. So it's going to be force times displacement times 90 degrees. 90 degrees is 0. Since the cosine of 90 degrees is 0, since the cosine of 90 degrees is 0, since the cosine of 90 degrees is 0, 0 times distance times force is 0. A vertical line, a vertical force can never cause a horizontal displacement. Though a vertical force does not do work on a horizontal displacement object, it can be accurate noted that the waiter had been pushed forward on the tray for a brief period of time to accurate its form rest to a final working speed. But once up to speed, the tray will stay in its straight line motion at a consistent speed without a forward force. And if the only force exerted upon the tray during the consistent speed age of its motion is upward, then no work is done upon the tray again. A vertical force does not do work on the horizontal displacement. A vertical force does not do work on the horizontal displacement object. So let's move. The equation for a work listed 3 variables. Each variable is associated with one of the 3 key words mentioned in the definition of work: force, displacement, and cause. The angle theta in the equation is associated with the amount of force that causes a displacement, as mentioned in a previous unit. When a force is exerted on the object at an angle to the horizontal, only a part of the force contributes to a horizontal angle to the horizontal displacement. Let's consider the force of chain pulling upwards and rightwards upon a feeder in order to drag a feeder to the right. It is only a horizontal component of a tension force in the chain that causes feeder to display to the right. The horizontal component is found by multiplying the force F by the cosine of the angle between F and D. In this sense, the cosine theta in the work equation relates to the cos factor. It selects the portion of the vector that actually the meaning of theta. When determining the measure of an angle in work equation, it is important to recognize the angle has Here's its definition. It is the angle between the force and the displacement vector. That's what the theta means. It's the angle between the force and the displacement vector. Sure to avoid meaningless using angles in the equation. A common physics lab involves applying a force to displacement a car by a ramp to the top of of a chair or a box. A force is applied to a chart to a displacement to decline the consistent speed. Several inclined angles are typically used, yet the force is always applied parallel to the incline. So let's the SI units for work. The SI unit for work is joule. Whenever a new quantity is introduced in physics, the standard metric units associated with the quantity are discussed. In the case of work and also energy, the standard metric unit is the joules, which is abbreviated in J, which is written as J, a capital J of course. 1 joule is equivalent to 1 newton of force, causing a displacement of 1 meter. In other words, a joule is a unit of work. 1 joule, so here, 1 joule is equals to 1 newton times 1 meters. And here is the equation. 1 joule equals to 1 n times meters. We have now standard units for work, which is ft times pound kilometers. In summary, in the summary of all the talking, in summary, work is done when a force is acted upon an object to cause displacement. 3 quantities must be known in order to calculate the amount of work. Those 3 quantities are force, displacement, the angle between the force and its displacement. Okay, thank you very much. See you next time.